Let me remind you where we were. What about linear response theory, which is a nice place to apply all the techniques that we've learned in perturbation theory and field theory. We said that we imagine a Hamiltonian, which is time dependent and consists of H naught, which is time independent, plus a perturbation V, which depends on time. And this V of t has a structure dx. This is some spatial integral. I don't have to think of a spatial integral, by the way. But if we're talking about a field theory, then we might as well have a spatial index. But for everything we're going to do, it doesn't really matter. And this phi here is our field. So for example, if you really want to imagine something, you can imagine that H naught is some integral dx over maybe some pi squared divided by 2m plus grad phi squared c m c squared over 2 grad phi squared. Yeah, a free harmonic field, but it doesn't have to be. And these are like operators. And then we said that our goal is to compute the average of some delta phi, which is phi minus its average without the perturbation, which would be some integral t prime dx prime chi of t minus t prime x minus x prime f of x prime. That's our goal. The goal is to obtain this chi, which is like a Green's function, if you like, for this specific driving. Yes.
What is the linear response? The linear in F or in phi?
You're asking what are we linearizing in?
Yes.
We're linear. First of all, you'll see it in a moment.
Okay.
We're linearizing in V or F.
Okay.
I don't know what exactly it means linearizing phi. We'll see.
Okay.
So then, I reminded you that we have, the Schrödinger picture, the Heisenberg picture, and the interaction picture. And the idea is something like this. So we have wave function evolution so we have something like t. You know what? Hold on. Let me make this table clear. Let's write it like this. So we have Heisenberg and interaction. So here we have two things. One of them is the evolution. So we have that psi of t Schrodinger is something like right, and operators are just constants. The Schrodinger picture, the Heisenberg picture is exactly the opposite. Psi of t is just psi. It's just a state. The operator O of t is something like right? But this is the time ordering operator. And then the last picture, which is the one we're going to use, is where O I of t, the operators, are evolved only with the free part of Newton, which means that the wave function is evolved by something quite more complicated. Let me write it like this. So we have psi interaction of t is equal to e to the I h naught t times e to the minus I integral dt prime up to t h of t prime times psi. Okay. So these are our different pictures, and what I was about to argue when we finished the previous class was that in this interaction picture, you actually evolve the wave function only using v. And now we're going to see that. So what I want to argue basically So let's look at this thing. Let's look at d to dt of psi interaction of t. So if I apply this on this wave function here, so this is basically d to dt e to the I h naught t e to the minus I integral up to t dt prime h of t prime psi of 0. Okay, now this operator here, it acts once on this thing and once on this thing. And assuming nothing here commutes, this gives us I e to the I h naught t. So I assume that h naught commutes with itself. That's a reasonable assumption. Therefore, I can move h naught to the right instead of left, and then I have something like this. Okay. Now I can stick here. E to the minus IH naught t, e to the IH naught t, because this is just the identity matrix. But you see that then, okay, and this thing is just V of t. Okay? So what you see here is that basically what we're doing with these operators here is we're evolving this phi. Instead of being just phi the operator, it becomes now a phi in the interaction picture. Actually, this is not a very accurate description, because when we write phi of t in this way, it's as if we decided that we're working in the Heisenberg. If we're in the Schrodinger picture, then this operator is not changing. Okay, so that's a matter of choice. This thing here should be taken with caution. But now we're only evolving it with h naught. So what we get is basically vi of t, which is the interaction in the perturbation in the interaction picture, and then here we're left with e the IH naught t. Oh, I forgot the t here. T. We have this t minus I t dt prime h of t. And notice that when the derivative acts on this guy, it just takes down h. That's another point. And this acts on psi of 0, but this guy is exactly psi interaction of t.
Interaction is just V, right?
V interaction is just V? No. What do you mean by that?
You will VI.
VI is when you evolve V with... Okay, so let me write. Let me add this. So this guy is e to the IH naught t v e to the minus h naught t. Now, the point is that v has time dependence, okay, coming from this guy, okay? But now we're also evolving. By the way, there's also something super confusing that I did here, because the t yeah, kind of V. Okay, I could have done everything in the Schrodinger picture, for example. Schrodinger picture, this would have just been a fixed operator. And then this would depend on time and do whatever. Okay? But here I'm dividing, and then I could also do it with a Heisenberg picture, and then these two would be fixed at the same time, given that I evolved this thing. But now I'm kind of I'm doing it halfway. So the point is that this t is indeed that t over there, but it's only evolved with a free part. And that exactly gives this guy becomes phi I. That's basically the point. Vi. So the end result that we get is that d dt, psi interaction of t, is equal to I v interaction of t, psi interaction. And that's this surprising result. So what it means is that in the interaction picture, we evolve the wave function just with the v, but the special thing, you could say, okay, but that doesn't make any sense, because that would be the case if your interaction would just be v, right? Exactly the same. But no, this is not just v, this is v in the interaction picture. That's the difference. That's where the free part of the Hamiltonian is hiding. Okay? Yeah. Good. Okay, so now the next step is to write the evolution operator. So we can look also at d to dt.
This is true even psi is not an eigenstate of the Hamiltonian?
Psi is not. This has nothing to do with eigenstates.
But if I multiply by I and h bar, it's an eigenstate of the Hamiltonian.
It's an eigenstate.
On the left side,
First of all, it's
I
already okay. It's already. First of all, which Hamiltonian? A Hamiltonian, which is VI. But first of all, I don't know what eigenstate means for a time-dependent Hamiltonian. Okay.
The Schrödinger equation, if I write the time-dependent Schrödinger equation, it's like minus h bar dollar dot t is equal to the Hamiltonian. And I don't know what this is. If I multiply by IH bar the equation, this is exactly what is written here. So,
Yes.
So
but
psi
it's
is necessarily an eigenstate.
no. First of all, again, what is an eigenstate for a time-dependent Hamiltonian?
If I will act with the Hamiltonian on the wave function and get some number times the Hamiltonian.
No. D to dt. First of all, the relation here, it doesn't matter if the I is here or here.
Yeah,
That's
of course.
The I and the H, and H bar is 1.
Yes.
We don't care about that. But this relation, okay, has nothing to do with eigenvalues. And if it would be an eigenfunction, that would imply that this is just IE.
Yes.
That's the point. And this, by the way,
The idea, but this is only true.
it's
Well,
it's no. So you can this can be a time independent Hamiltonian, and then you can diagonalize it and have eigenenergy. If you're in the adiabatic limit, then you can make an approximation about these energy states, which are like E of t.
Yes.
That's an approximation. That's not exact. Okay. So what is this? Okay. The short notations. I don't know why I didn't do this earlier. Let me define u of t as e to the I h naught t times this t e to the minus I integral up to t dt prime h of t prime. And then I want to look at this. And I want to claim as we've seen before, for exactly the same reason we had over there, this is going to be equal to minus I VI t u of t. Okay? And what this implies is, so we can do an integral on both sides, right? And therefore we can write on this side we get u of t minus, say, the identity, assuming that, you know, at time t equal to 0, nothing, there is no evolution, is equal to this minus I, an integral, let's call it dt1 up to t, vi of t1, sorry, t1, u of t1. Or in other words, we get the self-consistency equation that this is equal to this. Oh, sorry, this is now we can just plug this equation into itself, and we get that this thing is equal to identity minus I integral up to t dt1 vi of t1 minus the integral up to t dt1 integral up to t1 dt2 vi of t1, vi of t2, u of t2. Right? And then I can continue this again and again and again. And then there is this well-known idea that if we look at this expression here, then basically we're integrating over, over t2 and t1, and the point is that t1, right, is always larger than t2. So that means that basically we're integrating over this. Oh, sorry, no. Sorry, this. We're integrating over this region, right? And that gives us, half. And if we'll go to the cube, we'll get 1/6, and so on and so forth in the region. And this exactly gives us. So we could, add these other terms, and what we get is basically we can convert these into these factorial terms, and integrate over t1 and t2 over the entire plane, but then just make sure to time order them, because if they don't commute at different times, then it means that whatever is here is always later than what's here. That's important. And that's how you get this time ordering thing if you forgot. So this becomes e to the minus I integral up to t dt prime vi of t. That's our evolution operator. That's all I want.
This is some sort of transfer matrix.
Transfer matrix.
Like each process, like we're summing up over all these possible deviations.
Transfer matrix. I'm not sure I want to call this the transfer matrix, but maybe. I'll have to get back to it. I think it's much simpler and much more fundamental than transfer. Okay, good. So now that we have this, I want to do a perturbative and Oz, here is where the linear assumption is going to come in. Up to now, everything we did is so let's assume for a moment that the average of phi under its own Hamiltonian is 0. Then delta phi is just equal to phi of t. Then this thing is basically like asking what is psi I of t, phi I of t, psi I of t. And then we can use okay, and then this thing is equal to psi of 0 u dagger of t, phi I of t, u of t, psi of 0. But then we can use this relation. Basically, all I really need to linear order is these two terms here. Okay. So what I can write is that this thing is equal to, sorry, this is approximate. Okay, here is the linearity coming in. I'm going to write this is 1 plus I, the integral up to t dt prime, I of t prime, by I of t, 1 minus I, integral up to t dt prime, I of t prime, and psi of 0. And now, okay, so there are a few terms here. What we get, continuing it here, so I get basically psi of 0 phi I of t, psi of 0, that's the first term. And then to linear order, I get plus I, which are the mixed terms. So this is when this multiplies that, multiplies this, or when this multiplies this, multiplies that. So it won't surprise you that what we get is an integral up to t dt prime psi of 0 commutation relation of vi of t prime phi I t psi of 0, and then more terms. So that means that phi of t minus phi I of t is equal to minus I, the integral up to t, t2 prime, integral dx prime, so what I did is I plugged in V here. VI, in fact, VI. And if I look at this expression and I compare...
minus sign up there?
No, there's a minus here.
Okay.
This is a typical minus sign because we want a positive response, right? If there's a plus there, then when you apply the field in a certain direction, then let's say these are spins, for example. If you have B dot M, right?
Mm-hmm.
Then you apply magnetic field, and all the spins go opposite.
Okay.
So and you know this. You know when you derive, for example, the energy of a dipole in an electric field, or a magnetic dipole in a magnetic field, then there's a minus sign. Okay, so that's why we typically write this minus. Just makes sense for positive response. But it doesn't have to be. You could have easily the opposite sign. It's completely arbitrary. Okay, so if I look at this expression, it looks exactly like what I wanted. Okay, so I now have an expression for my susceptibility. And what you can see, one moment. Okay, let me write the susceptibility, then I'll take a question. Then we find from here that chi of t minus t prime x minus x prime is equal to I theta of t minus t prime, probably with a minus sign. Minus. The expectation value of the commutator of the fields evolved in the interaction picture. Okay, so this is a very simple and generic expression, which overall makes sense that the linear response is a property of the system, the dynamics of the system, that's controlled only by the free part of the. That's basically the definition of it being linear. Yes?
You have the average of the interaction of the phi in the interaction picture, right there.
I have the average of phi in the interaction.
In the middle equation, you have the average of phi. In the middle. Yeah.
This. Yes.
So you have the average of phi, and then minus the average of the phi in the interaction picture.
No. This. Okay. This is the real expectation value.
Yes. Okay.
This is the expectation value, assuming only the free part of the evolution. Right? Because let's look here. Look here. How do operators evolve under the interaction picture? They evolve only with the free part.
Yes.
Okay?
Oh.
So that means that this part I could interpret it, in the kind of Schrodinger picture. I could act on the wave functions, and you would see that here the wave functions are evolved kind of with a full Hamiltonian in this term, and here they're evolved only with the free part. It's not non-interacting. By the way, it can very well be interacting. It's just important to us that it's not. It's not it's not time dependent. It's not the probe field. Okay.
Although it depends on time.
It can depend on time because why can it depend on time? That's a good question. Now you're asking whether it will depend on time. That depends on the state and on the the initial conditions, which is the state and the operator that we're looking at. Okay, it can have some dynamics. If these are, for example, eigenstates, if you're evolving in an eigenstate, then it won't depend on time. But let's say you're not, you start not from an eigenstate, then it can oscillate.
Yes.
Okay, for example, if this is like a coherent state, then you can see it oscillate in a harmonic oscillator or something. It doesn't mean the fact that it's a time independent Hamiltonian doesn't mean that the dynamics, it can't have dynamics. Okay? How are we with time? Let's see. Okay, so let me make a few comments and then we'll go for a break. So the first comment I already mentioned is that the expectation value here is the expectation value with respect to some initial state, okay? And this initial state can be anything. We will typically focus on expectation values, where psi of 0, O psi of 0 is actually something like a trace over e to the minus beta h times O. Okay, something like that, which divided by some 1 over z. Which is actually not even, it's kind of like a mixed state. So we can even think of thermal states. You can kind of do whatever you want. The second comment is that you can see here that I wrote chi as a function of t minus t prime and x minus x prime. Okay? That reflects, as you've already learned, that there is a symmetry. Okay, so there's symmetry for translations in time and space. If there is no such symmetry, then it doesn't obey this relation, and then the situation is more complicated. In particular, we're going to use quite heavily the fact that we can transform this relation to Fourier space, right? And this, from the convolution theorem, that basically delta phi, okay, of omega at q is just going to be, in this case, it's going to be this chi of omega and q times f tilde of omega. Okay, and this relation is only useful or relevant if we have this symmetry. So that's another comment to make. And then okay.
Because only then momentum conservation is valid.
What?
Only then momentum conservation exists.
That's true. That's true. But it's just that if you don't have these translational invariances, then this kernel, this Green's function, ability, or whatever other name you want to call it, propagator, is not a function of a single parameter in each one of them, but two. And then this relation no longer holds, like it becomes more complicated. So of course you can generalize to those situations, but you need to apply caution. Because I'm teaching you, I'm commenting, you should notice this. Yeah, and the last thing I think I've already commented is that this chi, it doesn't depend on the drive in any way. It's a property of the equilibrium system. And that's one of the reasons, on one hand, you could say that this is like, if you went to the seminar we had today, I don't think any of you did. You did. Which is a pity. But if you went, then Ilya was talking about non-equilibrium states. And on one hand, you can say that this is kind of boring. Linear response is boring because it's just equilibrium physics. If you go beyond that, you can see more general, like you can see phenomena that doesn't, like, there's a richer, let's put it this way, there's a richer space of phenomena you might expect in non-equilibrium systems as compared to equilibrium systems. But the power of this implies that if we're in the linear regime with a probe, then we can extract a lot of information about the system. And when we start investigating a system, it's always best to start from the simplest things. The simplest things you can extract from the linear response. Basically, it's telling us that in the linear response, the probe is observing, is probing the system. It's a probe. Okay? It's not invasive. It's basically telling us something about the system itself, about its excitations, and not something about that is probe dependent. Okay. Yeah. So I propose that we go on a break, an earlier one this time, and come back at 4 and 5 minutes. Sound reasonable?
So that means that the very curvature and anything doesn't come into play at all, right? Here, in linear response.
The Berry curvature?
Yeah. It all
But
begins
like
when
a Berry curvature can come into play. As you know, for example, the Chern number is a linear response.
right.
So no, I wouldn't say. But if you're talking about Berry curvature of the field itself, like the field is, like Ilya was talking,
Yeah,
like
exactly.
the field induces some trajectory which causes some Berry curvature, then yeah, that won't. Okay?
Thanks.
Now we're going to talk about dissipation. Dissipation of energy. So the field that we apply is driving the system. The question is, how much energy is being pumped into the system? Okay? To do that, we're going to look at the excitation value of the Hamiltonian, which is the energy basically, and see how it changes with time. So I want to say that the power is E T equal to D to dt of H and this is equal to the integral of X dot x t times 5. Now
picture.
This is Schrodinger. That's a good question. Yeah, because naively, okay. First of all, it shouldn't depend on the picture. That's the first thing. It is true that, in principle, this expectation value also depends on time. Ask why don't I take the derivative of that as well? And there is a good answer to that. Which I don't recall right now. Hold on one moment. Let me see if I can remember. Okay, let's continue with what I have and get back to this question later. So we asked why not take the derivative of phi. But this phi is this expectation value is also constant. In fact, what I want to do is I want to plug this in within linear response theory.
Should give it a minus?
What?
The V comes with
minus. So then this guy is minus the integral dx. You could put a minus sign here. Then it's like asking how much energy is being pumped into the system, or how much energy is coming out of the system. Yeah, you're right. So the change in the energy of the system would be how much energy is pumped into the system. So one thing I have to remind myself. There's this question of whether d to dt of h is equal to expectation value of dh dt. So we're basically what we wrote here is like the expectation value of dh dt. That's
They descend because h commutes with itself, and then I can use the first theorem.
so you want to say that h dot is goes like h with itself, which is 0.
And plus, I mean,
plus
dou h
up to that, up to those. Right.
Plus the partial
Plus
derivatives to the
the
way.
yes. There is like IH bar. In the
right.
commutator.
That's a good point. So basically, this.
Yes.
Right.
Yes.
So that's probably the answer. Good. So so maybe let's write that properly. we're saying basically that this guy is equal to dh and therefore then we have what we said. We have minus dx f dot x t, the expectation value of phi. Now, for the expectation value of phi, we can use this expression. We have basically phi I. Sorry, we have an integral dx f dot of x t times phi I of t minus the integral dx prime, the integral dt, oh sorry, dx, minus the integral dx, the integral dx prime, the integral t prime f dot of x t chi of x minus x over t minus t prime x minus x prime f of x prime and t prime.
So why does it say that we don't derivative the expectance of phi? It's
Okay.
partial derivative of the h.
So let's say we want to take, so in this picture you can either you can take this derivative either with within the Schrödinger picture or the Heisenberg picture. So when we write this, we're talking about the Heisenberg picture.
Oh,
Na-
okay, and then you say the expectance value does not depend on t.
Yeah. Okay. So now we're left with this thing. Then
It's just using the as
Just
zero.
what?
so what does Ehrenfest tell us?
If
So-
you want to take the time derivative
Yes.
of any operator, you need to, and then you want to calculate the expectation value, you need to take the commutator with the Hamiltonian plus הנגזרת החלקית של האופרטור. הפשוט המפורשת בזה.
Right.
שפשוט גם איזה IH כבר.
Yeah.
So basically, what you're saying is that dh dt is equal to this. It's sorry, this is I. So we have I h with itself, which is 0, plus dh dt. Now dh dt in our case,
Exactly what you wrote.
yeah, but that's not clear to me because now we're talking about the Heisenberg picture. It is true that we're thinking about H in the Heisenberg, but in the Heisenberg picture, H itself okay, I'll have to clear this argument better, but from what I recall, when you take like the definition of this partial derivative is only the explicit dependence of h on time. This is what it means. It's not the internal dependence of h on time. But that's something I'll have to clear. Like I don't remember it from the top of my head. Okay. So if you believe that, so that okay, that's like a kochavit for me. Okay, I have to clear that away next lecture. Okay. But putting that aside, then here, okay, here, this is already not exact. This is an approximation, right? Because this is like linear response. Okay. Now we're going to make a definition. So I define chi double prime of, say, r and tau as so this is like x minus x prime and t minus t prime. Sorry, I switched their places sometimes. So I define this chi double prime to be 1/2 the expectation value of phi I of x and t, phi I of x prime and t prime. Okay, so this is just without the theta function. So here you can see the definition of chi, here you can see the definition of chi double prime. So that implies that chi of r tau is equal to minus 2I theta of tau chi double prime of r and tau. So that's something we're going to use later. That's a definition. Okay, and we'll see in a moment how it helps us. Now on top of this, let's assume a monochromatic drive. So I assume that f of t is something like 1/2 f omega e to the I omega t plus f star omega e to the minus I omega t. And I neglect the spatial dependence. So that implies that this second part here, you see here, is basically an integral from minus infinity to infinity t prime f dot t chi of t minus t prime f of t prime. This I can rewrite as this guy is minus omega over 2, the integral from minus infinity up to t dt prime. So this guy, you see, it gives me this omega factor and the I, but this I I'm going to absorb in this definition here. So, and the theta function made the integral from minus infinity up to t. So I get f omega e to the I omega t minus f omega star e to the minus omega t. And the minus here is because we took the time derivative. Then I have chi double prime of t minus t prime, and here I have f omega e to the I omega t prime plus f omega star e to the minus omega t. Okay. Now I can open up all these expressions, and I get two types of terms. I get terms that are like f omega squared e to the I omega t plus t prime minus f star of omega squared e to the minus I omega t plus t prime. Sorry, this is and then I have the cross terms. Plus 2 times I sine of omega t minus t prime f omega star. Now, okay, good. And I forgot something. And then this whole thing is multiplied by chi double prime of t minus t.
When you take the derivative, shouldn't you have an I somewhere?
This derivative.
Yes.
Yeah, but you see this definition I made here?
Yeah, okay.
So I switched here from chi to chi double prime, and I needed to
Oh, okay.
absorb this back.
Okay.
So now what I want to argue is, let's say I write P average as the integral 1 over say omega over 2 pi, the integral from 0 to 2 pi over omega over dt p of t. So I average it over a cycle. Okay, and what I want to argue is that because everything is periodic here, then these terms, they must vanish under this average. The reason would be because it would be like saying that so shifting both t and t prime is like starting the right. Basically, there is some time t at which I am observing the system, and there is this time t prime at which the force acted. So if I shift them together, and look at the same quantity, I don't expect it to depend. This is a physical assumption. So I want to argue that this part actually it's it averages out. So it would be like writing integral. So I have something like omega over 2 pi, integral from 0 to 2 pi over omega dt, the integral from minus infinity up to t dt prime of whatever I have there, which is like minus omega over 2 erase this. And I have 2 times I sine omega times t minus t prime f of omega star times chi double prime t minus
What happened to f dot time phi interaction? Hope it's not small lemma.
f dot. No. Right. So, yeah, I'm assuming that this also vanishes under this average. Because, okay, why? Because this is like the free part. Yeah, that's okay. So I don't know it. What?
Can't you see it from the equation? Like,
You can probably see it from the equations. Let's see first of all if I have something written down here. Yeah, I'm certain that you can show that this is I'm certain that you can show that it vanishes because the free part of the Hamiltonian how could I see this?
maybe אינטגרציה לחלקים. והעבר שפה הוא 0 מהמחזוריות שלה.
So let's say I plug in this relation here.
Okay.
Then it's phi I. Yeah, so there is in principle some like remember that this is evolving under the free part of Hamilton,
Right.
which could have all sorts of frequencies related to the internal dynamics of the system. But the chances that it would have a frequency that exactly matches this frequency would be so yeah, you might get some delta function. I need to think about that. But in the general case, assuming that there is no resonance or anything like that, it would just average out to 0. So
Maybe it's just like the what happened to the cross terms there.
Well, you could. Okay, that's what I was trying to say. Like phi could have, I could write it also as some frequency dependent thing, and then if it's exactly resonant with something, it might give a response. But I don't think that's very interesting. So basically what it means is that only phi omega equal to 0 gives you a response here. That's a good question. So that's another thing for me to clear out next lecture. But okay, but let's see what we have here. So first of all, let's see I did everything properly. Okay, so now let's see. What did I want to say now? Oh, okay.
Can I ask
Yes,
now?
yes.
Even if the power is zero, I mean the average is zero, it doesn't mean you do not pump energy to the system. Even if I want to check the voltage of the wall, I need to take the RMS of the voltage, not the average. If the average is zero, it doesn't mean that there is no physics that take into account.
No, I think okay. The question is, what are we looking at here? That's actually not true, because if you're looking at the power of the total system you have, and half of the time it's positive and half of the time it's negative, it means that half of the time it's absorbing energy and half of the time it's emitting energy.
Okay.
So if you like, of course you're right that, you know, if you're, say you're driving a system and this happens to you, then you will feel that you're pumping in energy all the time, because it's not going to lose energy exactly back into
Right.
your drive, right? It's going to lose it to some environment, or at least it could. But that's yeah, but actually that would require, let me think about that for a moment. That would require some sort of conversion to some other degrees of freedom. I don't think, yeah, here we're just looking at the overall power, the amount. So we're looking technically at the absorption of the system itself. If the system itself has, you know, the average of P is 0, it means the system is not heating on average, for example. Okay?
No,
So
I can't understand it, because
why?
it's not true for, let's say, the power grid. I mean, if I take a light bulb and connect it to the wall,
Yes.
it's power,
Right.
it's heat, but the average power of the wall is 0. If when I take a fluke and connect it, it calculates the RMS.
No, if you look at the power in, so let's take a light bulb, for example, like the old school light bulb or a resistor. Then first of all, you need to acknowledge the fact that there is a heating process, and then there's the steady state.
Okay.
So in the heating process, where it starts to heat up, then the power is not 0. The power is it's I times V. So you get, you know, despite the fact that the current is oscillating back and forth, power is you're pumping power into the system all the time. It's not true. And that's why we pay we pay money.
Okay.
So that's, but it is true that you know, like, there is some truth in what you're saying, because we're gonna see it in a moment. Okay, but just to conclude, okay, so now something is missing in my argumentation. made a mess with this. Okay, I want to look only at this part. Okay. So basically, this was to argue that these terms fall out on average. So they don't contribute anything on average. They're there, they oscillate, okay, but they don't contribute anything on average. But if I look only at this part, which is the part that doesn't average out, then I can write that minus the integral from minus infinity t dt prime of minus omega over 2 times I sine omega t minus t prime f of omega star chi double prime of t minus t prime. We can change the variables to be an integral from 0 minus to infinity d tau, where tau is again it's t minus t prime. Omega over 2 e to the I omega tau oh, sorry. Let's not jump ahead of ourselves. This is an integral from 0 to infinity d tau sine of omega tau. Here we have minus omega over 2. Zero to infinity d tau omega over 2. The 2 and the omega cancel, so let's just write omega. Then we have I sine of omega tau chi double prime tau f omega star. Okay. Now
how did you make why is it,
how did I make what?
why is it from 0 to infinity?
Because I changed variables. Integral is no longer over t prime, it's an integral over tau, which is a difference. Okay? It's a minus, it's supposed to be minus?
No, it's fine.
Okay. Now, what I want to argue. Okay, so this thing I can open up into an integral from 0 to infinity d tau omega, and then I have over 2, and then I have e to the I omega tau chi double prime of tau minus e to the minus I omega tau chi double prime of tau. Okay? Now I want to argue that chi of tau is equal to minus chi of minus tau. And how do you see that? You see it from this commutation relations. Okay? So that means that I can, okay, let me continue here. It means that I can rewrite this thing as minus an integral from minus infinity to infinity omega over 2 e to the I omega tau chi double prime of omega f omega star.
Don't you have over 2 from the sign?
Yeah, omega over 2. That's
No, but this was already there. So
No, it wasn't. It wasn't
It
because
was
I had
2n.
I had a 2 because of the two terms. Okay. So, oh, sorry, this is tau. This is tau. So now I can just perform the integral d tau, and then this thing becomes minus omega over 2 f star omega f omega chi double prime of omega. So the claim is, okay, so what does this mean? It means that the power has, so overall I can write that the power has some oscillatory part. Oscillatory part plus a part. Oscillatory part, which is uninteresting, plus this thing. It's like minus omega over 2 f omega star f omega chi double prime of omega. That's the end result. So what is this telling us? It's telling us that whatever this chi double prime is, which is this correlation function, it's actually the Fourier transform of this correlation function, is what dictates how much dissipation is in the system.
This is actually perform also the second, right?
No. So yeah. So this is okay. So here I cheated a little bit. So this argument was just to argue why I'm neglecting these terms. But when I wrote this, I wrote an expression only for this part. And that's why, if you really look at P, there's an oscillatory part. Okay? But the constant term, which is, the damping that's always occurring, is basically proportional to the field squared, okay? Which is kind of related, I think, to what you were trying to say before, times this chi double prime. And in a moment, we'll see that chi double prime is, in fact, the imaginary part of chi of omega. Okay, so basically what I want to argue is that chi double prime is the in frequency space. Okay, and this is important, is the imaginary part of chi of omega, and where chi of omega is the transform Fourier of this guy. Okay. So in real space and time they have this relation, but in Fourier space they have this relation. I didn't show this yet, okay? But it shows you, but this is a very important relationship between the imaginary part of the Fourier transform of the response function and dissipation. Okay, that's the first connection that we make. And you see that the larger this chi double prime is, the larger we're going to have more and more dissipation. And you can already feel now our next step is going to be fluctuation dissipation theorem. But you can see that this is indeed like a fluctuation. So you can already smell this fluctuation dissipation theorem. The stronger the fluctuations are, the more dissipation we're going to have in the system. But let's make this connection formal. And I need to reply like these two. Just to review, I need to clear why this is the derivative of h, why only this term. And up there we had another issue, which was, what was that issue? I don't remember. I'll look it up in the technique. Okay.
I think it was about the second part of the power.
The second part
Yeah,
of the you mean the linear term?
Yes.
Right. How to show that it vanishes. Right. We're talking about Not that it vanishes, but it basically doesn't contribute a constant term. It contributes maybe at most an oscillatory term. Okay, so now we're going to talk about fluctuations. So we define the structure factor as the expectation value over delta phi of x and t, delta phi of x prime and t prime, okay, which is by definition the variance, okay? This is basically, and this delta phi is not yeah, okay, so what do I mean here? So now this average is assumed to be thermal. So I promised you before that we can use any expectation value we want, but in this specific case we want to think about a thermal average. So what we get is 1 over z trace of e to the minus beta h delta phi of x and t delta phi of x prime and t prime. Okay, and this guy is equal to 1 over z trace.
This is h with the interaction. With the
yeah, that's a good question. No, well, everything we're going to consider is going to be within linear response.
Okay.
So, okay, you can't even define. Yeah, I should write here h0.
Okay.
You can't even define thermal equilibrium if you're out of it.
Yes.
So it's no, most definitely not. So the only effect of the field is coming in these fluctuations. So this thing we can write delta phi. In fact, I would even say more than that. I would say that right now, this delta phi here, I want to think about it as phi minus phi. Okay, and everything here is computed within equilibrium. So the motivation for that is exactly the expressions that we had. I wiped them off the board by now, but you know, using this response theory, yeah, that's a good point. So using this response theory, we saw that the response, the linear response, is depends only on equilibrium expectation values. So now everything I'm saying about fluctuations is in this equilibrium. Okay. So there is no field.
Even though the system is outside the system.
No field. No. It's more than that. It's more than that. Right now I'm talking about fluctuations. Fluctuations.
No external field.
No external.
Okay.
Okay. So this thing is like e to the beta h0, e to the minus beta h0 delta phi.
This comes from the fact that the susceptibility is not dependent on the field, right?
This comes from the fact that the susceptibility. Yes. Well, you know, this motivates us to discuss for a moment the fluctuations in the ground state, because we saw that the fluctuations in the ground state are related to are related to the response. Okay, and now I want to make that connection formal.
Okay.
So you could write here I, okay, if you want. But we're really thinking about fluctuations in an equilibrium system. So that's why I'm omitting this I. But if it helps you, you know.
But basically, the susceptibility can depend on the field, right?
Oh yes, but that won't be within linear response. That would be beyond linear response. Most definitely it can. It can and it will. Right?
But why can't I treat it with linear response, even though susceptibility can be? If I think, let's
why can't you treat what?
If I think, let's say, on a thermal conduction, so
Yes.
kappa is dependent on the temperature, which
Yes.
is the field.
No. First of all, that's not the field. The field is the gradient.
Okay, yes, that's that's the same.
No, it's not.
Why not?
It's not the same because you're treating your linear. First of all, thermal transport is extremely delicate. The gradient of temperature is not exactly a field. It's in the full sense of the word. It's not like your Hamiltonian has a term like I wrote, where you have
Right.
you know a gradient of
Yes.
temperature couples to some field.
Right.
Okay, so that's complication number one. But on top of that, you are thinking of the gradient of temperature as a field, and then you're expanding in gradient of temperature, and everything you're calculating. You calculate thermal conductivity is equilibrium expectation. Okay, so Tzvi, just to fill you in, all of these fields that we wrote, if you feel comfortable, you can denote them with an I, because we're evolving everything just with a free Hamiltonian. Okay, right now we're talking about fluctuations in equilibrium, and I want to connect it to these response functions. Okay, but because this is a no field situation, I can even omit the I. It has no meaning. Okay, so now I wrote this thing.
What do you mean by no field, no interaction, no?
So in the beginning of this class, we wrote H as H0
Yes.
plus some V.
Yes.
Now I'm thinking of a system without
Okay.
V. I don't care about V. V doesn't exist. I'm talking about a system at thermal equilibrium.
Oh, okay.
Okay?
Okay.
Okay, I'm just going to make statements about the fluctuations of this system and how they're related to the response of the system.
So here delta phi is like something else then.
Yes, exactly. That's what I wrote here. Delta phi is really the deviation from the expectation value. So if phi has some expectation value, I don't want to take that into account. I want only the fluctuations. So this thing really gives me the fluctuations. This is like spatial temporal fluctuations. Okay? And then I can write that this thing is 1 over z trace of delta phi of x and t plus I beta e to the minus I beta h0 delta phi of x prime and t prime. Now I can use the cyclic property of the trace. So this thing is equal to 1 over z, the trace of e to the, there's no I, minus beta h0, delta phi of x prime and t prime, delta phi of x and t plus I beta, which is nothing but the expectation value of delta phi of x and t, delta phi So what this is telling me is that the expectation value of x and t and then x prime and t prime is related to the expectation value of x prime, t prime, and x and t with this shift of I bit. Okay. So so that implies that s of x minus x prime and omega, which is equal to the integral dt from minus infinity to infinity e to the I omega t, wait a second. Yes, good. Okay, good. Okay, let's call this tau. Tau. S of x minus x prime tau. This we can switch x, so this thing is going to be equal to the integral from minus infinity to infinity d tau e to the I omega tau, and then we have s of x prime minus x, and then we have minus tau minus I beta, right? Because this is like t prime minus that. That's okay. And now we can we can make a change of variables. Okay, so let's say we call this guy tau tilde or something. Okay, and you allow me to shift the integral slightly, right? You're not going to be, you're not going to care about that. This is equal to e to the beta omega, the integral from minus infinity to infinity, this d tau tilde, I omega tau tilde s of x prime minus x and tau tilde, which is e to the beta omega s of x prime minus x times minus wait a second. Sorry, let's call this minus.
You shifted the x and x prime on purpose.
What?
You started with x minus x prime. And
Yes, of course, because look at this relation. This versus what I started.
Ah, okay.
Right? I switched. So that leads me to the relationship which is basically some sort of detailed balance that s of x minus x prime omega is equal to e to the beta omega s of x prime minus x and minus omega at thermal equilibrium. And now we can use the definition. Now use the definition of chi double prime to write chi double prime of x minus x prime and omega. What's going on with the crows?
Close this one.
You know that my cat, he's like this vicious bird killer. It's really annoying because he always brings us dead gifts. Yeah, gifts. Yeah, but by the way, a horrible thing is that, like, I had a lot of cats in my life, also a few dogs, but most of them would just, they would kill something, play with it, and that's it.
Right.
But this guy, he really eats them. Like so it looks like the Godfather or something. You have this, this thing like completely dismantled in front of our front door. And the funny story is that actually I had this neighbor who, I had a crazy neighbor. I still have this crazy neighbor who decided that he is going to fight the pigeons that are pooping on his, I don't know, like his mahsan, how do you say, like this shed. So they would sit on the window, like the bottom of the window, how do you call it, the ledge, window ledge or something.
Okay. Yeah.
And he didn't have access to that because there was a window, like a closed window. So he broke the bottom of the window and started sticking all sorts of objects to prevent them from sitting, which was completely stupid because some of the objects he took was just like, what you have on top of the gas stove, like this black thing, and that's like perfect for them to stand on. It's like more room for us, but he still thought, so he tied these things like an old person. And I told him, look, you can't do this. This is dangerous. There are kids walking around. This could easily fall on one of their heads. Says, no. Said, look, if you're not going to take it off, I'm going to take it off. And then he got really angry, and I took it off. And he decided that from now on, I'm to blame for all the bird shit he gets. So one day, we were traveling, and my neighbor sent me a picture that he took all of the bird shit and just spilled it on our door. And that's that. I managed somehow. Today I got him under control. That's like a different story. But then the funny thing is, then our cat started dismantling birds in front. The first time she came back and saw a beheaded pigeon on our front door, she was like, "Oh my God, the neighbor went like next level. He's like totally Godfather." And I'm like, no. I wish it was the neighbor. Yeah, so that's my stupid cat. But why am I telling you this? Because every time it goes on the roof, like the pigeons are stupid. They just do. But the crows, they go like wild. They start warning each other. And you know it from like a mile away because you can hear them. So I think there's like a cat somewhere on the roof probably. They're now trying to warn each other.
What?
Huh? Yeah. So anyways, this you can just use the relation that we had before, because it's a commutation relation. Okay. And now using this relationship that we just found, you find 1/2 1 minus e to the beta omega s of x minus x prime omega. So this is what is known as fluctuation dissipation theorem, this relationship. And it's a very deep relationship because it tells us that, so first of all, it works only in thermal equilibrium. Fluctuations that are very weak, close to equilibrium. And it tells us, what does it tell us? It tells us, so first of all, it shows us, it now makes the connection between this structure factor which quantifies spatial and temporal fluctuations in frequency space, and the dissipative part of the a response function. So, and that's a very deep connection, because if you think about it for a moment, it tells you that if there's a lot of fluctuation in a certain frequency, okay, it means that the system can absorb a lot of energy there. It's very soft. If you like, the system is very soft, and therefore it can absorb a lot of energy. And that's the connection between fluctuation and dissipation. And this term, what it basically tells us is that there is some relationship, like temperature can cause transitions, back, which counter the behavior. And this is this term here. So in the limit where you take, wait a second, did I get that right? No, sorry, this is with the minus.
It makes no sense.
Okay. Otherwise, it would be insane. Yeah, maybe did I get the previous one right? So yeah, so the point is that you see these are like excitations at frequency omega. This is at minus omega. So the relationship between these two terms is like absorption and emission. So once the system is at a finite temperature, it can also emit, and therefore the balance between the power that you put into the system and how much it heats up is kind of taken out of balance by temperature. So in the limit where you have a lot of thermal fluctuations, say you take beta to 0, which is like taking temperature to infinity, then the system is no longer absorbing any energy. It's going wild. That's what this is telling you. That's another important consequence. And then the last thing is that it turns out that this is somehow related, and this is like some deep connection to the second law of thermodynamics, because it implies in some sense that if you dissipate, it's telling us that dissipation inside the system, which is like heating, is going to fluctuations. And fluctuations imply an enhancement in entropy, because you have more fluctuations, more entropy. So it kind of, the fact that this relationship exists implies kind of close to equilibrium, that you can't, enhance the amount of fluctuations, but extract energy or something like that. So there's a relationship between entropy and work. Okay, so
can I ask a question?
yes.
So in the proof, when we define the
Chi double prime.
Yeah, chi double prime by the commutator of phi interaction. But here you have like commutator of delta phi not interacting.
Yeah, but they're the same thing. Again. So let's focus. If we have a finite drive, then the interaction picture for operators implies that you evolve them only with a free part of the Hamiltonian.
Yes.
Okay, so that would be the same evolution you would get in the system at equilibrium if there wasn't a drive.
So why here you have a delta?
You're asking, I don't understand the question.
Then you have the commutator of phi. Here you have the commutator of delta phi. Yeah, maybe it cancels. Maybe I don't know. Maybe it cancels in the commutator.
Okay, so so you're saying, okay, so let's go back.
Yeah, I think maybe just cancel.
No, it's fine. It's a good question. So you want to say that the way we defined chi 1/2 the commutator of phi I of x and t and phi x prime and t prime. And you're saying this is not delta phi I, but phi I.
I think when we wrote it, we assumed that the average of phi is 0. Therefore, the
Yeah,
delta phi is equal to phi.
okay, hold on one moment. I think it's not a problem. I think it's not a problem because this is a commutator. So if these guys would have some expectation value, it would fall out of the commutator. So you see this relationship here? If I would write it in full, so I can Fourier, okay, so let's say I write something like delta phi, now in real space, of x and t, okay, minus delta phi, sorry, I write something like this. You see, I write something like delta phi of x and t, delta phi of x prime and t prime, minus delta phi of x prime and t prime, delta phi of x and t. I want to argue that this thing, so this thing has a couple of different types of terms, but so let's start. When we take the expectation value over all of them, they're all numbers, so they commute, and then you get 0. Okay? Now there is the term that gives you this, which is what you want. And then there are the mixed terms. So what do we have with the mixed terms?
I think it also goes to 0 because it commutes, like the average is numbers.
Yeah, exactly. So overall we get the same. So the point is that it's a commutation relation. Okay, good. So now the last thing I want to discuss, how am I with time? Okay. So the last thing I want to discuss is the analytic properties of the response function. So the statement is this. We state that chi of t smaller than 0 is chi of tau smaller than 0 is 0 by definition. By the way, I didn't even mention this, but this is causality, right?
Yeah.
So the question is, what does this causality imply for chi of omega, right? So I know that chi of tau smaller than 0, which is equal to 0, is the integral from minus infinity to infinity d omega over 2 pi chi of omega e to the minus I omega tau. Okay? But if I, imagine that I think of a complex plane where this is the real part of z is like omega, and this is the imaginary axis of z. Okay. Then, if tau is negative, then and I'm performing this integral. Okay, and I know that this integral should give me 0. Right. So what I claim is that I can complete this integral, like I can add this segment to the integral when I take so let's call this segment 1 and this segment 2. So this is basically segment 1. But I want to argue that segment 2 is also 0 because tau is negative. So if z develops a term that is also like so okay, let me write what I want to write, and then we can argue about it. So I want to argue that this thing is also equal to an integral dz over 2 pi chi of z e to the minus I z tau. Okay, and then if z develops a positive imaginary part, this thing is exponentially decaying. Okay, so it implies that now, and that would kill this segment, this arc.
So you can take the radius to infinity.
Yeah, I'm taking the radius to infinity. So what that tells me is that in this entire regime, okay, there are no poles. So that means that chi of z is analytic in the upper half plane. Right? So this is basically the crucial analytic property of chi, which is a result of causality. And we can exploit that in many different ways, including showing that chi double prime is the imaginary part of chi of omega.
It's like the Fourier transform of chi, right?
Chi of z.
Yeah.
It's the analytic continuation of the Fourier transform of chi. Good. So now, so let's. So what we want to say is so I want to define function. Comment about analytic functions. So I want to use the following definition, that f of omega is equal to 1 over I pi, the integral from minus infinity to infinity, rho of omega prime divided by omega prime minus omega minus plus I epsilon the omega.
Can I ask this question?
Yes.
About the last comment?
Yes.
Even if the integral is 0, maybe there are two poles that cancel each other or something like that. You need to sum over the poles. It not necessarily means that there are poles, right?
Let's see. So you're saying, what if chi of z has two simple poles of equal weight.
Yes. The opposites.
Wait a second, but the integral that we're performing is not over chi of z, but chi of z times e to the minus I z tau.
Okay.
So let's try and analyze what you're saying. Let's assume that the residue. So basically, you're asking what is the residue, okay, of this chi of z. E to the minus I z tau. Okay. At z equals to z naught, where this chi of z has some pole. So that would be the limit of z goes to z naught, z minus z naught times chi of z e to the minus I z tau. So this might have a residue, but then we have this phase factor. So
but I think he's claiming like that there is non-analytic functions with zero integral and this contour.
even with that phase factor? I don't think so. So that's okay. For sure. Okay. For sure. You know, if you're thinking about an integral, dz over 2 pi of some function f of z, okay, and that's 0. That no one promises you, and this is this thing. No one promises you that f of z is an elite.
Oh, that's the question.
Right?
Yes.
But here I have this phase factor.
Okay, why it's promised me that sign?
Okay, because then what I'm going to get is I'm going to get chi. Let me call it r chi at z naught times e to the minus I z naught tau. Okay. Now let's assume I have two of those. They need to cancel each other.
But if chi has a phase also that cancels out exactly this phase, so you can have
Chi has phase.
if chi is the f you wrote there times the phase, then it cancels.
No, but if chi has that phase cancellation, then I would argue that the integral doesn't go to 0 anymore when
Yes, okay, that.
Yeah, but maybe okay. Maybe we should sharpen. I wonder if I wrote them. I think I have a more elegant argument here. Let's see. So, moreover, we may look at the direct Fourier transform. Limit of z going to infinity. Right to infinity. So in fact, it's finite, and the Fourier transform exists, but it decays exponentially to 0 at z going to infinity. In the upper. This argument. Okay, let's continue next week. What we have left to do in linear response theory is I want to show you a Kramer's Kroning relation that these because of this analyticity, you know that analytic functions, they have a special relationship between the real and imaginary part. And this is a very useful way. So many times people would do absorption experiments and infer, something about the non-dissipative part of the response function, or vice versa, do a reflectivity experiment and infer something about absorption, and so on and so forth. So this is a very powerful experimental tool that's called Kramer-Kroning relation. That's one thing, but the only challenge is that it requires us to know the entire frequency dependence of chi of omega, and typically in experiment or in calculation you would only have a finite range of frequency. That's one thing. Then we're also going to talk about another crucial thing, very crucial for our course, is to make a connection between Matsubara response functions. Response functions. So, the calculation of Matsubara response functions can be done here on this imaginary axis, and how we can relate that to real frequency response functions. Let's see if I have any other. I don't remember if there's anything else. And then we'll move to the next part of the course, which I don't even think I've decided yet. But we said maybe renormalization, right? Let's do RG. Okay? Hey, good. So, have a nice weekend. And somehow I survived another lecture.
ChatGPT אומר שיש פונקציות כאלה.
שיש מה?
שיש פונקציות כאלה שהן האינטגרל על החצי מישור העליון נותן 0, אבל הן לא אנליטיות.
זה ברור.
לא.
לא, אבל עם הפאזה, כאילו עם ה-E וה-I.
שהן לא אנליטיות ב-upper half plane.
כן, שיש איזה פונקציה xi של z, e במינוס i z t.
יש לו דוגמה?
אז הוא נתן דוגמה שאני עוד לא הספקתי לבדוק אם היא נכונה או לא.
אוקיי.
אולי הוא טעם, אבל הוא טוען שיש.
זה תיאוריה מאוד יסודית, אני גם עכשיו.